G'day cobbers, welcome back to the bush. In this episode of Lockouts for All Driving, we're looking at Anderson plugs and whether they should be crimped or soldered for the electrical connections in the back of your four-wheel drive. We're looking at crimped, we'll be looking at soldered, we'll even be chucking in crimped and soldered. A little bit of column A and a little bit of column B. Let's get into the testing. So in order to pull off a successful Anderson plug crimp, you're going to need a bit more than a piece of wire and the Anderson crimp. You're going to need a pen. You're going to need a cable stripper, preferably not a knife. You're going to need cable cutters and you're going to need the crimper itself. So we start off by just getting the end of this and squaring it off in our cable cutters. Hopefully to the right length. Okay. Then we line up our Anderson end to roughly about the depth you want it and just mark off the cable with a felt tip pen where you'd like to strip back to. Okay, now these are adjustable on depth. You can again do this with a knife, preferably not, because it scores the conductors and then will lead to a fatigue point later on. So preferably you get these cutters and you just run them around once and then run it off the end, and then you can find the cut and just with a fingernail peel it off. Rightio, and usually comes out nice and neat. Beauty. Alright, next one up, we just test fit the connector onto the end. That's all done. Now you need to make sure you're using the right mandrel in your hydraulic crimping tool. Now in this case, I'm using the 10mm because that seems to work just fine. So then you put the crimp into the crimping tool, make sure it's locked down solid, and just crimp away. Now once it starts grabbing the connector itself, usually I push the wire in home a little bit and then just keep pumping until it locks down solid. And it will, and it'll actually go into bypass. Okay, it's nice and tight, so we can back off the pressure and that's it. Our crimp is done. We've got a nice tight crimp on the end of that cable, and I'll zoom in a bit so you can have a decent look. And there we go. There's the crimp, successfully completed. Next up, we'll show you how to do a solder joint. Now for soldering. So in addition to the wire and the connector, you're going to need a couple of other things. You're going to need some way of holding onto that connector when it gets hot. You're still going to need to strip the wire. You're going to need to mark the wire. You're going to need solder. You're going to need cable cutters. And you're going to need some way of heating up that connector so the solder will flow. And I'm going to use a butane torch, though you can use a heavy soldering iron. Okay, so just like before, let's neaten off the end with our cable cutters. Now with that done, we need to strip it back. So just again like before, line it up and mark it off. Now comes the turn for the strippers. So let's put the stripper onto the cable and run it around, and let's peel that back. Just simply peels back with your thumbnail. Job done there. Let's test fit it, make sure it fits okay, and that's not too bad. Actually, I might trim the end just a touch. Let's test fit it again. Yep, I'm pretty happy with that. Now you need to get your connector and put it into your lockjaw pliers. Okay, with that done, and this is definitely not the chopping board out of the kitchen. If the GLW sees this video, definitely not the chopping board, okay? I will appreciate that if you don't tell the GLW this is the chopping board that I prepared the chicken for dinner on. Okay, alright, let's start heating it up. Okay, now we've got that connector nice and warm, we'll feed in some solder. I think it could use a little bit more heat. Let's try that now. There we go, that's a lot better. And you don't want to overfill it, you want to get it about half to 3/4 of the way full. Okay, if the flux is coming out the top, it's obviously too full. Okay, so now just insert that cable into the connector and hold on to it for a minute or two to make sure you get a decent solid connection. Okay, now it's cooled down sufficiently that we can actually release it from the jaws of the lock nose pliers. And as you can see, we've got a tiny little bit of solder stuck on the connector there, so we'll just blast that off. And there we go, it's job done. Okay, next up, crimped and soldered. Now for crimped and soldered. So I've already taken the liberty of crimping this end on, and I've also drilled a small hole in the top here so we can feed in a bit of solder. So what I'll do is I'll heat him up. Now with that heated up, I'll feed the solder into the hole at the top. Carefully, trying not to run it all down the sides. I'll give it a little bit more heat. And a tiny bit more solder. Well, it's flowing out the top now, as you can see, so I don't think I'm going to get any more solder in there. So we just let it cool down now, and that's both crimped and soldered. What you don't want to do is solder first and then crimp, because you won't be able to squash it down effectively using the hydraulic crimping tool. So if you are going to crimp and solder, make sure you crimp first and then solder. But it might be useful, it might not. The results will bear out on this one. So now I've got my 3 samples here, crimped, soldered, and crimped and soldered. I've got my multimeter here. Should simply be a matter of putting that on ohms and testing. But what about the materials these are made of? Well, mostly copper in this one, copper and solder in this one, and copper and solder in this one. So what about the resistivity of the materials we've used in the construction of these terminations? Let's check it out now. Now let's check out metal resistivity. On the left hand side here we've got the metal resistivity in ohms per metre. And along the bottom here, the 3 we're going to look at. First up, aluminium. Now that comes in at 2 by 10 to the negative 8 ohms per metre. Now for those who aren't familiar with scientific notation, in decimal all this means is 0.702. Okay, so it's a very, very, very small number. Moving on, copper. Copper comes in at 1.68 by 10 to the negative 8, so it's slightly more conductive and has slightly less resistivity. Finally, solder. Now this is your usual tin lead alloy 60-40 split, and that comes in at 17 by 10 to the negative 8. So it's considerably more resistive and considerably less conductive than either copper or aluminium. In fact, as far as resistivity is concerned, it's nearly 912% worse than copper. So straight out the gate, it's fighting an uphill battle. Now, all of these numbers, even solder, are a very, very, very small amount of resistivity. So does it actually make a difference in a practical application? That's the question we're going to answer today. And now we know all about the materials, it should simply be a matter of putting our multimeter into resistance mode, grabbing our leads, and putting them across the various connections. Or is it? Is the 2-wire resistance measurement method the one we're after? Or is there a more accurate way to measure extremely low amounts of resistance? Let's check it out. So here's our conventional 2-wire resistance measurement works with a digital multimeter. So we have our resistance here, which is resistance DUT. DUT means device under test, and at this point we don't know that it's 10 ohms. The multimeter is turned on and in the resistance setting. So it injects a known current into the unknown resistance. Once that known current is established in that unknown resistance, it then measures the voltage back in the multimeter. Then it uses a little bit of Ohm's law to calculate the resistance. So it does the voltage divided by the amperage. Now in this case, it measures a voltage of 0.1 volts over the injected current of 10 milliamps and gives you a resultant 10 ohms and displays it on the display for you. And that works fine for most resistances until you get into very low resistances. Let's have a look why. Now let's have a look at the issue when you're trying to measure a very small amount of resistance using the conventional 2-wire resistance measurement method. Firstly, contact resistance. And of course there's 2 points of contact there in between the probes and what you're actually trying to measure the resistance of. So it's going to vary, and that's an unfortunate compounding issue. So it's going to vary depending on contamination. So there might be a bit of oil from your skin on those probes. It also will vary with the amount of pressure you're putting on those probes to the resistor leads. Now to compound that, we also have the resistance of the leads themselves. So they're not made of superconductors, so they actually have a bit of resistance. And that's all going to be measured by the digital multimeter. So what your resultant measurement on your digital multimeter is going to be your DUT, or your device under test, plus 2 times your resistance of your contact, plus 2 times your resistance of your lead. So we're actually measuring everything in the line there. So let's get an actual multimeter. I'll pick on one, I'll find one and I'll pick on it in a second. We'll rip out the specifications and we'll see what it's going to do in a practical application. Now the multimeter I've chosen to pick on is a Fluke 117. Reason being, it's a commonly available high quality multimeter where the specifications are readily available. And of course we've set it to ohms to measure resistance. Now again, our resistance, our DUT, our device under test, 0.5 ohms. This time though, we got our contact resistance, 0.2 ohms, which is a fairly common contact resistance, and our lead resistance of 0.4 ohms. And of course we have 2 of them. So our measured resistance on our multimeter will be 0.5 plus 0.4 because we got 2 contact resistances, and 0.8 because of the 2 leads. Okay, so that gives us 1.7 ohms. 1.7 ohms when we actually got a device under test of 0.5 ohms. So that's an issue. Now you may well be saying to me, Simon, we'll just zero out that meter. And the way you do that, of course, is to get your 2 probes, you push them both together nice and firmly, and you press the zeroing button or the null button or the delta button on your multimeter. But there's an issue with that. It decreases the accuracy markedly of a multimeter, and let's show you how. And here's why you shouldn't use the delta, zero or null functions on your digital multimeter whilst measuring small amounts of resistance using the 2-wire resistance measurement method. Now our DUT, or our device under test, just like before, 0.5 ohms, our contact resistance, 0.2 ohms each, and finally our lead resistance, 0.4 ohms each. So our total resistance in that circuit there, because they all add up, because they're in series, is 1.7 ohms. Now our quoted accuracy of this digital multimeter whilst measuring resistance is plus or minus 0.9%. So if we're measuring a total in series resistance of 1.7 ohms, that gives you this figure here, plus or minus ohms. Now, if we zero it out and we're measuring 0.5 ohms, our accuracy doesn't change. It's still plus or minus this figure here that we got for the 1.7 ohms. So instead of 0.9%, it's now gone up to plus or minus 3.1%. And that is 244% worse. Is that acceptable to you? Well, it's certainly not acceptable to me. And there's a way to mitigate this, and it's called the 4-wire resistance measurement method. Let's have a look at that. And here we have it, ladies and gentlemen, the piste resistance of low resistance measurement methods, the 4-wire resistance measurement method, otherwise known as a Kelvin connection. Now it looks unnecessarily wieldy and a little bit complicated, but it isn't really when we break it down. Now, first thing to admit, there are desktop bound multimeters which can pull off this connection without a second multimeter or a regulated power supply, but I don't have one of them, so this is how I'm going to do it. Now firstly, we have a look at this multimeter here, and it's set to amperage, and all it's doing is measuring the amperage in this circuit. And we have this multimeter here, and it's set to DC volts, and all it's doing is measuring the voltage across DUT. Okay, now we know that, let's break down this circuit. Okay, so we have contact resistance, just like before, 0.2 ohms, and then we have the lead resistance of 0.4 ohms. Now you'll notice I've got
10 milliamps, 0.01 amps coming out of this regulated power supply at 1 volt. If we use Ohm's law and our resistance here, we're going to measure across DUT 0.005 volts or 5 millivolts. Now, if we plug that into the impedance, and we can find that in the specifications of the multimeter, of 10 mega ohms. So our 5 milliamps over our 10 mega ohms equals 5 by 10 to the negative 10 amps, or 5 nanoamps. It's getting very, very, very small. Now, if we want to work out the voltage drop in the lead, all we need to do is add up our resistance, times it by our amperage, and there we have it. There's the voltage drop in the lead, 0.6 nanovolts. We can pretty much ignore it at this point. It's so infinitesimally small. It's not going to affect the reading over DUT. Okay, so that's how it works. That's how we get such accurate results of resistance. But of course, because we've still got the 2 meter readings, we're going to have to do a little bit with Ohm's law afterwards. But we can get around that, or maybe plug it into Excel. Okay, well, that's the theory. On with the practice.
Okay, and while all that theory is fine, let's actually measure a solder joint. So this is obviously the solder joint. Now I've got a power supply on the left hand side, and that's supplying 2 amps, 1 volt, and you'll be able to see the amperage on this meter here. That's applied to either side of the joint. These two are measuring the voltage drop via the mushy meter outputted onto the display. We'll zero that display so we get an accurate voltage reading. There we go, 0.000 or thereabouts. We'll turn it on, and you'll be able to see 2 amps here, and we got, what's that, 0.513 of a millivolt. Okay, that'll do before I blow anything up. Let's move on to the next one. Okay, now this time we've got exactly the same setup as when we tested soldered, except for this time it's crimped and soldered. So let's zero out this meter here to make sure we're getting accurate reading of voltage drop over these 2 leads here. And there we go. Let's give it 2 amps, as you can see on this meter here, and let's check the display and see what we're up to. There you go, about 0.5 milliamp, about the same. Move down to 0.2, see if it's going to fluctuate at all. 0.3, 0.568. Okay, that'll do. Let's move on to crimped. Okay, here we go. Exactly the same setup as before. Let's zero out that meter and wait for it to settle down a second. There we go. Let's give it 2 amps and see how we go. So again, 2 amps, 1 milliamp, and we're getting actually a higher resistance. Well, a higher voltage drop at least. Alright, well, that's the results. So let's consult George Simon Ohm and check out what the resistance values are for the various crimped and soldered connections. I'm quite surprised by this figure.
And here we have the final word. Soldered versus soldered and crimped versus crimped. Now on the left hand side here we've got the resistance in micro-ohms ranging from 0 right through to 1000. Along the bottom here we've got our 3 test subjects. First up, soldered. Well, that came in at a mighty 256 micro-ohms. Next up, soldered and crimped. Well, that came in at slightly higher at 284 micro-ohms, so slightly worse. And finally crimped. Well, that came in at 934 micro-ohms. I couldn't believe the result. In fact, I ended up doing all 3 tests 3 times and averaging. Got the standard deviation to make sure that I had true and accurate results. And these are the results. This is the data. This proves beyond any reasonable doubt that crimping, as far as resistivity is concerned, is considerably worse than either soldered, crimped, or soldered. In fact, crimping is 365% worse than soldering as far as resistivity is concerned. I'm amazed. I really am. Okay, but what does that mean in a real world scenario? Let's say we're running 100 amps through a connection, through an Anderson connection powering something like an inverter. Okay, they're rated to 120 amps, the SB50s, are commonly known as a 50 amp Anderson. So no problems running 100 amps through them. I've done it many, many times. How much energy are we wasting per termination? Well, as far as crimped is concerned, we're wasting 9 watts. Not a lot in comparison with the 100 amps we're pushing through there. Soldered and crimped, 3 watts. Soldered, 2.5 watts. So I don't think this should be your defining factor, because as a percentage of the overall energy you're pushing through the Anderson, it's not a lot at all. Even though in this graph it looks considerably worse, and it is. But in comparison with the overall energy usage, not too much at all, really. Now, there are other factors to take into consideration. What about vibration resistance between soldered, soldered and crimped, and corrosion resistance over a long term in between these three joining methods? Well, if there's enough interest, drop a comment below and I'll get to that video as well.
So what do we think in the end? Well, as far as the Anderson plug and resistivity is concerned, looks like soldering is your best option over crimping. Okay guys, now if you like this video, don't forget to give it a thumbs up, and if you didn't, by all means, give it a thumbs down, not once, not thrice, but twice. Thanks guys, we'll see you in the next one. Now where's my crimping tool?